At the beginning of each term, I start with some kind of notion of how the grades are going to look. So, for example, in this sheet, I might say, okay, well, based on the difficulty of the course and the kinds of things I've seen in the past, this is what I expect to have happen. So I've got A, B, C, D, and F here, and in this column I have what I would expect. So I expect to give out 10 A's, 30 B's, 30 C's, 20 D's, and 10 F's. Okay. So let's say that I have established those expectations, and then I look at my grade book at the end of a particular term, and I see that this is actually what I have. And what I might want to know is how different are these? So have I fulfilled the university's expectation of a grade distribution in this particular term? So I want to say, well, okay, it looks like I've got approximately the same number of A's. It looks like I'm short of B's here, kind of high on C's, and the D's and F's are kind of close. But once again, we want to formalize this intuition, this observation, so that we can quantify the magnitude of the difference between the expected number and the observed number, and then decide whether that's significant or not. Okay, so once again, we have a situation where we can do a hypothesis test about whether observed values are different from expected. So it turns out that when you're trying to look at the difference between an expected discrete distribution and an observed discrete distribution, there's a well-defined test for doing this, and it's called the chi-square test. So the chi-square test tells us that all we have to do if we want to find out whether whether our observed values are about what we would expect is we have to take this number right here. We just have to take our and I'll just write it out here to make it a little bit easier to know what these symbols mean. So we're going to have the difference between observed and expected. Okay, I know that doesn't make it easier, but so we've got a difference between the observed and expected. This is what this O means here. This is the observed, and this is the expected. And we're going to take that square distance, that squared difference, and we're going to divide it by expected. Okay, so this O stands for observed, and this is expected. Okay, so we take the difference between this and this, square it, divide it by this, and then we add all these up. Okay, and we're going to get a number that follows a chi-square distribution. I'll go into more detail about what this is in a minute when we try to find out the p-value associated with a particular chi-square statistic. But for now, let's just go ahead and compute this and see if this distribution is significantly different. So I'm going to add a column here, and I'll call it I'm going to call it expected or squared difference divided by expected. Okay, so this is going to be equal to the observed minus expected, and we'll square that, and we'll take that whole expression and divide it by the expected. Okay, so observed minus expected squared divided by expected. Okay, now we'll do that for each of these. We see that the A's are not off by much, but the B's and C's are off by by a lot. And so what we want to do is add these up. Okay, so we'll take the sum here equal to the sum of all these. So we have this is our chi-square statistic. Chi-square statistic. And the name comes from the fact that this is a Greek letter. Okay, so this is the Greek letter chi, and then it's pronounced, I guess, K-Y-E. So it's chi squared. Okay. All right, so it's a chi squared statistic, and you remember that we had. So we're getting more and more of these, statistics now, and we had our z, which was a two-tail, right? Or it could be two-tail, and we had our t, which had two tails, so it could be positive or negative, positive, negative, positive, negative. And then when we were doing an ANOVA, we had an f statistic, which only had one tail and could only be positive, and it looked like this, where we would have some kind of, we're interested in this area, and this area would be our p-value. Okay, once again, we got a situation where we're interested in a distribution like this, which is only positive, but we're going to allow it to, not have this particular shape. Now, it turns out that the F statistic actually derives from the ratio of certain non-negative variables. This chi-square that we have, the one tail, is, it's only going to be positive, but it isn't necessarily shaped exactly the same as F, because in some cases it goes down like this, in some cases it swirls a little bit differently, but it is going to be non-negative. Okay, it's going to be one tail and it's going to be positive. But because of the nature of the data generation process, it's not going to be exactly the same as F. So we have to use a chi-square statistic. Now, once again, I'm going to just show in in Excel just a little bit of a reminder. When we were trying to find p-values, we had, if we were dealing with a normally, a z statistic, we did norm.dist, okay, and this took an x value and returned probability, which is what a p-value is. And then we also had a t-dist, which took a value and a degrees of freedom and returned probability. When we were looking at, assessing whether an F ratio was significant, we did f-dist, and it took the F statistic value, and then also the numerator degrees of freedom and the denominator degrees of freedom. Well, this is just one more. It's exactly parallel, and it's chi-square dist, and it's going to take an x value and degrees of freedom. Okay, so in this case, our chi-square statistic was this 4.817 here. It's the sum of all those squared differences of observed and expected minus divided by expected, and then the degrees of freedom. Similar to other cases that we've seen, our degrees of freedom is going to be equal to n minus 1. So in this particular case, our n was 5. There were 5 different grades, so our degrees of freedom would be 4. And of course, we have to type in true. Okay. Now, remember that we are interested in the area to the right of this tail. So one thing we have to remember to do is to do 1 minus. So this is actually our p-value. Okay. And let me chop off some of these decimal places so that I can read it a little better. Okay, so p-value. So what this is telling us is that the difference between the observed and expected has a 31% chance of 31% probability of occurring by chance. So this tells us, this is a large p-value. This tells us that we don't really have enough evidence to say that these are significantly different. Okay, so our observed and expected seem to be close enough that we can't reject the possibility that they are different. Okay, so we would say in this case that these appear to be the same distributions. Okay, so the grades are the same as what we would expect. However, what if I were to move 7 of these A's over to F's, and so this is now 2, and this is now 19, we see that p-value changed quite a bit. We've got a chi-square statistic that is much larger now, and because the difference is much greater, and we got a p-value of 0.001. Okay, therefore we would reject a null hypothesis that these two distributions are equal. Okay, so this is roughly how it works. So anytime we have a distribution and we want to compare whether observed values are close to expected values, then we're going to do a chi-square test. So we're going to do that chi-square statistic, which is the sum of all the squared differences divided by the expected values, and we're going to add them all up and find the p-value. Okay, I'm going to run through another example in a minute, but just so we get back into some hypothesis testing theory, let's take a look at what the null hypotheses would look like on a test. But I'm going to do this. Okay, I'm going to do this by showing a particular test. Now, we're using the chi-square test in this case. So the chi-square test lets us examine whether whether an observed distribution follows an expected distribution. And so this is the general case. I used to have an exercise in class where we would open up bags of M&Ms, and we would be given a distribution of how many what percentage of reds we should have, and greens, blues, and browns, and then we would actually observe, and then we would see if if there's a significant difference between the distributions. So, but there's another and more a more generally useful in business contexts application of the chi-square test, and that is it provides us a way to test whether two categorical variables are independent. So examples of categorical variables are whether lateness versus shift. So first shift, second shift, third shift, these are these are categorical variables. And then late versus not late. Okay, so that's a categorical variable also. And if you want to see if those two are independent, then you can use a chi-square test. Another example of where this might come up is particular machine. So you have machine A, B, C, and D, and you want to see whether the actual machine and the tendency to to produce defect versus non-defect, that again is a categorical variable. So we can see if machine is independent of producing defective products. Another thing is a supervisor versus an incident. Okay, there might be a safety incident, and that's did a safety incident happen? Yes, no, and you could see if that value is independent of supervisor A versus supervisor B. Okay, so we have all these cases where we have categorical variables and we want to know whether they are independent. Well, the chi-square test lets us do that with this same kind of framework of where we are setting up an expected value versus an observed value, and then we see how different those two things are. And we can do this with a two variable test of independence. Okay. So, to begin with, if we want to, let's start off with an example, actually. Okay, so we would like to know whether handedness, that is, whether you are, left versus right-handed, is independent of gender. Okay, so this is going to be male versus female. Okay, now it's an interesting question. You know, there may not be any kind of physiological reason why your gender might cause you to be right or left-handed, but it is something that we might want to check. Okay, so we've surveyed 300 people, 180 male, and we found that 12 females and 24 males were left-handed. So conduct a hypothesis test on whether handedness and gender are independent. Okay, so this is exactly the sort of the test that question that I would give on an exam. And so once again we're doing a hypothesis test, and a hypothesis test, of course, always begins with hypotheses. So if we are testing handedness and gender, what is our null hypothesis? Okay, so we want to know. Okay, so within males, there's going to be a proportion of left-handed to right-handed. Okay, and in females, there's also going to be a proportion of left-handed to right-handed. Okay, and really what we want to know is, are these proportions the same? Okay, so we're going to call this proportion, the proportion for one group. Proportion sometimes is denoted with pi, or p. So proportion 1 equal to proportion 2. Okay, we don't have any directional hypothesis here. We just want to know if these proportions are equal. So if you're doing a chi-squared test of the independence of two categorical variables, we're going to do a null hypothesis of proportion 1 equal to proportion 2. Okay, so that's the null. Okay, so that makes the alternative then simply that proportion 1 does not equal proportion 2. Okay, so and then our second step, of course, we have to define our acceptable type 1 error rate, so 5% again, and we've already got our n. Okay, we've got 180 males. We'll do, we'll just go ahead and, when defining our n, we'll do our n1 and our n2. So we've got 180 males, and it's 300, so it was 120 females. 120 females. Okay, so now we need to decide, well, what is our, we have to decide our distribution and our test statistic. And in this case, because we're going to be doing an observed versus an expected, it's going to be a chi-square statistic. Okay, now well, we'll deal with more of the actual value later. Let's go ahead and start setting up the expected versus the observed in for this particular case. Now, what I like to do is to go ahead and set up these two different tables. So I've got gender here on the left, female, male, and the hand left and right. So now I can just fill in my observed, and then I have to think about, well, how many would I have expected? Okay, so let's see. We said that we surveyed 300 people, so it's a 300 total down here, and 180 male. So this would be 180, which means we had 120 females. Okay, and we said we had 12 females who were left-handed. Oops. And we had 24 males who were left-handed. Okay, so we can fill in the rest of this. Okay, so this total down here is just going to be 36. And if 12 were left-handed, how many were right-handed? Well, this is just going to be that minus that. Okay, probably could have done that in our heads, but that 180 minus 24, because these are collectively exhaustive. You're either left or right-handed. Leaving aside the case of ambidexterity. Okay, and so now this is just going to be the sum of these. Okay, so it looks like we have 36 left-handed people, 264 right-handed, and so we've got our observed table all set up. Now what we need to do is figure out what would be the expected. Okay, once again, we're going to have these this 300 down here in the lower right. But what we need to do is figure out, okay, if it really is the case that handedness and gender are the same, then under the null hypothesis, the proportion of males and females, the proportion of males who are left-handed is going to be equal to the proportion of females who are left-handed. So that would mean that, so I have my overall proportion right here, right? 36 out of 300 people were left-handed. So this gives me my overall proportion. So I'm going to write this, just write this over here. My overall proportion of left-handed. Okay, and so that meant overall 36 out of 300 people were left-handed. Okay, so what this would mean then is that, so 12% of people are left-handed. So if it is the case that these two, handedness and gender are independent, that would mean 12% of females would be left-handed and 12% of males would be left-handed. Okay, so that's what this P is here. So this proportion, so these proportions would both be 12 out of 100 or 36 out of 300. Okay, so let's go ahead and fill in then what would be expected over here. Okay, so remember that we had 120 females and 180 males. Okay, so what would be our expected number of left-handed females? Okay, so that would be 120, 12% of 120, right? Because that's the overall proportion. So this is going to be equal to the overall proportion times how many females we had. Okay, so we would expect then, given that they're 12% overall, that 14.4% of females are left-handed. And once again, to do the right, and we would just do the same thing. We would do 120 minus whatever we had over here. Okay. Now I know that it doesn't make any sense to have 14.4 left-handed females, but this gives us, more precise what we would expect so that we can see how far we are from that. Okay. All right. So likewise, we would expect 12% of the 180 to be left-handed. So we'll do, overall proportion times that 180. Okay. So we would expect 21 males. Okay. And then this is just going to be that 180 minus that amount. Okay. And these sums we don't really they should be the same because of the way we're calculated, but we can figure that out. Okay, just be the sum of these. Okay, and then the sum of these. Okay. Okay, so these marginal values then are all the same, but now we have a different set of expected. Okay, so we've got our tables filled in with our observed versus our expected. Now what we need to do is calculate our chi-square statistic. Okay, and remember that our chi-square statistic is going to be the sum of all these observed minus expected squared divided by expected. Okay, so let's go ahead and do that. So the chi-square statistic is going to be equal to, it's going to be a big sum. In fact, maybe what I'll go ahead and do is do each of these blocks separately. So, so this observed minus this expected squared divided by this expected. Okay, so there's going to be 4 of them. I'm going to fill them in here. And I'm going to fill them in separately, and then I will add them all up. Okay. All right. Okay, I'll put them in here. All right, so in this cell, I'm going to do, okay, observed minus expected squared, and I'm going to divide that by expected. Okay, all right, so that's left-handed females. Okay, so now once again, I'm going to do observed minus expected squared divided by expected. Okay, same thing here. So observed minus expected squared divided by expected. Observed minus expected squared divided by expected. Okay, so I've got all those. Now I just need to add all these up. And this will be my actual, this will be my chi-square statistic. So it's going to be sum, and then I'm just going to hold down control. So just add up those 4 numbers. Okay. Now, once again, we're in this situation where we have calculated our test statistic, and we need to be able to know whether this is, significant, if this is in the rejection region. So remember that our statistic, our distribution looked like this, and we need to know the probability of, we need to know that given this value, so let's say this is 0.75, what is this area over here? Because this is going to tell us the probability of this having occurred by chance. Okay, so we want to find the p-value corresponding to this 0.75, and remember that we do this with 1 minus the chi-squared dist. Okay, and then we put in our value, in this case 0.75, and then we need to do our degrees of freedom. And when we're doing the chi-square test of independence, degrees of freedom is always equal to 1. Okay, so I'm going to write this fact here. Degrees of freedom for this particular test is equal to 1. Okay, so now I just need to find, okay, what's the p-value of this statistic? So it's going to be equal to 1 minus chi-square dist of this, okay, degrees of freedom, 1, cumulative true. Okay, All right, so the p-value is 0.38. Okay, so what do we draw from this? Okay, so this means that there's a 38% chance of observing this when the proportions are equal. Okay, which means that our conclusion is fail to reject. Now let's go back to figure out what is it we're failing to reject. Okay, so we go back to our actual hypothesis test. Where is it? Okay, so our hypothesis test was testing the null hypothesis that the proportions are equal. So the proportion of left-handed females is equal to the proportion of left-handed males, and we have failed to reject this. Okay, so just to finish up our hypothesis test. So to finish up the hypothesis test, we have our conclusion, our statistical conclusion is fail to reject. So our so-called managerial conclusion is just that the proportions are equal. And when the proportions are equal, then that means that the variables are independent. They have nothing whatsoever to do with each other. And so there are just as many left-handed, the proportion of left-handed females is the same as the proportion of left-handed males. Okay. All right. So there is how you would go about doing a hypothesis test for a test of two independent categorical variables using the chi-square statistic.